So once we've transformed the series, if that was necessary, and we have identified if we need to take a difference or two differences and determine the possible orders of the P and Q parameters, then there's the estimation. The estimation, I mean, in the software is very easy. We just say SARIMA and then the model and the estimation occurs. Now, but that's what's behind this estimation of the parameters. The method that's used to estimate the parameters is maximum likelihood. So we use the fact that the assumption is that the ATs, the white noise, are independent, identically distributed as normal with constant variance. Okay, so the joint multivariate density function of AD plus P plus 1, AT plus P plus 2, and up to AN. And why do we start in D plus P plus 1? Because if I have P autoregressive terms, so that means that I have dependency from my observation at time t to observation time t minus 1, time minus 2, up to time t minus p. Okay, and then we have d differences because I lose d observations when I take d differences. So I start with the observation with the random noise starting at d plus p plus 1, all the rest up to the last data point that I have, or to the last white noise that I have, okay, which is the AN, assuming that we have capital N data points. So the joint density of this thing is multivariate normal with the ATs are independent. So the variance covariance matrix is going to be a diagonal matrix that has just the variance in the diagonal. And this will be the joint density function of the ATs, the white noise. Now, remember, we are considering that WT is already the dth difference. We already take the differences there of the transform series. So if we needed to transform, we already transformed, and then we work with the differences of the transform series. And it is the transform series, the one that we're going to model. So since WT is equal to this thing here, then AT, we can express the ATs in terms of the Ws, okay, of the transform series already differenced, and the ATs in the past with their parameters, with the theta 1, theta null is the constant, theta 1 up to theta q. Now, the joint density function then of the Ws, of WTs, is the density function, the joint density of the ATs times this will be the product of the derivatives of WT with respect to AT, and that will be this function here, okay? That this is going to be then the density function for the joint density for W d plus P plus 1 up to the Wn, which are the n data points that we have available after we take into account the P terms that in the past and the D terms that we lose when we take the differences. So this will be the joint density of the of W's of the series, which is what we observe. We observe the WTs. Okay, so we see then the likelihood function will be the function of the parameters given the WTs. That's the definition of a likelihood function. So the likelihood function L of the parameters is a function of the parameters given our data. Okay, so the function of the parameters given our data is this expression here, 1 over 2 pi to the n minus d minus p divided by 2, and sigma to the n minus d minus p. This comes from the normal distribution, we'll divide it normal. And then we have a term which is essentially the sum of squares of the ATs. This S of phi, theta null, and theta is the sum of squares of the AT squares, the sum squares of the ATs. Okay. And that sum of squares is this sum that we have here. All these things squared, and maximizing the likelihood. Okay, maximizing the likelihood is equivalent to minimizing these sum of squares. Okay, so to maximize the likelihood, we need the procedure is we first choose the values for the parameters that minimize these sum squares, and then we estimate sigma squared. So the algorithm, the way it works, it takes this likelihood function, assuming normality. That's what we check the assumptions later, the assumption of normality. Takes this likelihood function, which is the multivariate normal distribution, and optimizes that likelihood, minimizing the sum of squares of these AT squares, okay, of the AT. It takes the sum squares, minimizes that, and once we have the minimum value for this thing, then we use that to estimate sigma squared, okay? Because we can use then replace that minimum value here and solve for sigma squared to get the estimate of the variance of the ATs, okay? And that's the procedure. So first, the parameters, the Q and the P parameters are estimated, and then we estimate sigma squared. Now, the maximum likelihood estimator of sigma squared, it can be shown that is the sum of squares of the ATs divided by n minus d minus p. That would be the maximum likelihood estimate of sigma squared.
Oh.
However, we don't use this estimate. We use the unbiased estimator, which is the same thing, but we subtract in the denominator, we subtract also we subtract all the degrees of freedom. We have n minus d minus p, but we are also losing q and one more degree of freedom for the estimation of the constant. So the logic here is the same, the same logic that we use when we estimate sigma squared in the univariate case. Remember, in the univariate case, when we have a sample, and we have a sample xi, which are IID from some normal distribution of whatever normal with mean mu and variance sigma squared, we estimate the MLE estimate of sigma squared is equal to the sum of xi minus x bar squared divided by n. Okay, but the estimate that we use is normally s squared, which we denote by the sum of xi minus x bar squared divided by n minus 1. And we divide by n minus 1 instead of n so that the estimator is unbiased. Okay, because of this thing has a high square distribution, and to make it centered, we subtract the n minus 1 here to make it unbiased. So it's the same logic that is used here. We divide by the degrees of freedom. These turn out to be the degrees of freedom for the estimates of the parameters and also for sigma squared. Now there's no analytic solution to maximizing the likelihood function. Okay, there's no way to analytically obtain the maximum, so we use numerical methods. So numerical methods are used to maximize the likelihood function. That is, numerical methods are used to minimize the sum of squares and then estimate sigma squared. Now, since we use numerical methods, then the algorithm also needs some starting values. In the very old algorithms, and I'm talking about let's say 1978, around 1980 or something, when you wanted to do the estimation or the time series model, you needed to compute your initial values by yourself. I mean, you wrote a simple Fortran program to do that thing. Now the algorithm does that. by itself, and because it needs initial values to make sure that the algorithm converges in a reasonable number of iterations. So for example, for an AR1 or an AR2 model, we can get the initial values from the Walker equations. And we would get for an AR1, the initial value for phi1 would be the first autocorrelation. And for an AR2, the initial value for phi1 would be the first autocorrelation times 1 minus the second one divided by 1 minus R1 squared. And the initial value for phi2 would be this one here. We got this from the Walker equations that we saw when we studied the autoregressive models. Okay. In the case of the MA models, the moving average models, the relationship between the autocorrelations, the sample autocorrelations, and what will be the initial values of the parameters are nonlinear. So we would need to solve. Here it's a simple linear system of equations, and that's it. We get the solution. In the case of the MA models, it's a nonlinear system of equations that need to be solved to be able to find the initial values for the MA parameters. Let me silence. Okay, no, that's it. So when we want to estimate the initial values for the MA parameters, there are multiple solutions, but only one of those solutions will satisfy the invertibility condition. Okay, so there will always be more than one solution to find these initial values, but the algorithm will choose the initial values that satisfy the invertibility condition. Okay. For example, if the model is an MA1, then the first autocorrelation is theta tilde, which is the initial value, let's say, of theta, divided by 1 plus theta tilde squared. Now, from here, we get the solutions for theta tilde we have two solutions. We have minus 2 R1 to the minus 1 plus the square root of this thing here. And the other solution is minus 2 times R1 to the minus 1 minus, these are the two roots, plus or minus this term here. Now, they satisfy the fact that theta times theta prime equals 1.
Pasó mi jefecito. Oye, ya te mandé lo de Imex y me estaba diciendo Banamex que ya tienes que cambiar la clave.
We didn't receive the
bancaria, empresarial.
Let's see. That's it. Okay. So that's an example for an MI1. So these conditions satisfied. So only one of the two roots will be less than 1 in absolute value. And that's the root that's chosen as an initial value for theta. Okay. Now for an ARMA PQ, we have both a set of linear equations that to be solved and a set of nonlinear equations to be solved to get the initial values. Okay. And the procedure would be, if it's an ARMA PQ model, we first get the initial values for the P autoregressive coefficients based on the Walker equations, and then we use those estimates of the initial values for the phi coefficients to get the initial values for the MA parameters. Okay. Now, there is a potential problem with estimation is what's called redundancy. And redundancy consists on the existence of approximately common factors in the AR and MA polynomials. Okay, so if the AR and MA polynomials have approximately common factors, then that would lead to instability in the solution, in the estimation of the parameters. Okay, let's look at an example. Look at this model: 1 minus 0.3 b minus 0.2 b 28 b squared. WT equals 1 plus 0.4b AT. So this will be an ARMA. This is an ARMA 2-1 model, right? This is an ARMA 2,1 model. Well, we can write this in model as 1 plus 0.4b to the minus 1 times 1 minus 0.3b minus 0.28b squared times WT equal to AT to the white noise. So, and now this polynomial here, we can factor it, and we obtain that that's polynomial is equal to 1 plus 0.4b times 1 minus 0.7b. So this cancels with this one here, and we get 1 minus 0.7b WT equal AT. So this is an AR1 model. So we have two models which are essentially the same because the way we can factor this polynomial here. Now, if we were to estimate this model, we would get instability in the parameter estimates because we're in some sense we're overestimating parameters. If you look at this thing, this model is parsimonious, whereas this one is not. Here I have three parameters, phi 1, phi 2, and theta 1. And I can achieve the same thing with a model with one parameter, with a phi, an autoregressive parameter here. So the fact that and now this is exact common factors, but it's enough that we have close enough common factors to get a simpler representation, and then that will give us instability. So that we should always look for, when we are in the process of identifying and estimating models, we should always look for parsimony. And there may be, if we do this thing, we may get reasonable results when we check the residuals, but the parameter estimates will not be stable. And so we need to find out if there's another model that's more parsimonious. ARMA 2-1 model is still very few parameters, but if we can get a simpler model, that's what we should aim for. Okay, so that's what I'm saying there. The second model is parsimonious, and if we try to estimate the first model, what happens is that AR and the MA terms, this and this, they compensate. Okay, because essentially one of them is a multiple of the other. So since one of these polynomials is a multiple of the other, they will compensate and will cause instability in the solution. And sometimes when we fit a model in R or in another solver, we may get the answer that the algorithm did not converge. This could be a cause of non-convergence when I'm fitting the wrong model, and since I have an instability in the solution, what that is reflected upon in the estimation procedure is that the algorithm may not converge in a reasonable number of iterations. Now, validation, we've talked about validation. Essentially, all validation model will be based on residual analysis. We'll have to check mean zero for the residuals. We need to check that we have constant variance. We need to check independence. And remember that since how we check independence in the residuals, we looked at the ACF of the residuals. Normality, and that's why we use the normal probability plot of the residuals. We need to check that there are no outliers. There may be one or two, but it would be mild outliers, let's say. If we get something very, very, very extreme, we'll see that in the residuals, and we need to find out why in that observation we have such a big outlier, such a large outlier. Okay? And then parsimony. We should always aim at having a parsimonious model. Admissibility, that's essentially going to be guaranteed by the algorithm, because starting with the initial values, it will also start with initial values that are admissible. okay? That is, that satisfy stationarity and invertibility. And parameter stability, if we have high correlation among the estimated parameters, then that's very likely that we have instability in the estimates. Okay. So those are the checks that we're going to make. And all is based on the residuals. There's another thing that we'll talk later. If I have two models that look reasonably well, both models look well in terms of the residual analysis, and both are very close in terms of the number of parameters they have. Maybe one has two models, two parameters, and the other one has one. If the residuals look fine, we will go with the more parsimonious model, okay, with one. But if they have the same number of parameters, for example, then there's another criteria that we will use to select the model. And the criteria that we'll be using later is, we will imagine I have my time series here. Okay, and I will cut my series, let's say here. I'll cut it here, and then use the past, from this point to the past, to estimate the model, and then I will forecast this part here. And since I know the true values, then I can estimate here the mean prediction error. I'm gonna call it correctly, mean square prediction error. Okay, that will be the average of the squares of the prediction errors, because we know the actual values. Okay, so I'll write it down here, mean squared prediction error. And that'll be essentially the difference between my prediction minus my real for this part of the of the data. So I'll start from I equals to, let's say that this point here is, I'm going to call it capital T, from I equals to T, from T to N. Okay, this thing squared divided by N minus 1. By N or by N minus 1, doesn't matter. Here, it doesn't matter if it's an unbiased estimate or not. Okay. Essentially, that's the way we compare models that are equally that equally represent my data equally well, and have the same number of parameters. We will choose the model that minimizes the squared prediction error. Now, to verify independence, given that independence implies no autocorrelation, we should verify that residuals autocorrelations are statistically indistinguishable from zero. Okay, that's what we should do. Now, recall that the sample ACF of the residuals is given by this expression here. It's the A hats are are essentially the residuals, okay? Because those are the way the estimates of the A's of the white noise are the residuals. So I take the residuals from T equals to T prime to N minus K, multiply AT plus 18 plus K, and divided by the sum of squares of the ATs. That's my estimate of the autocorrelation function for the residuals. And we already know that if the true autocorrelations are zero, then the standard deviation of the standard error of R sub K of A hat is going to be 1 over approximately. So this will be approximately the standard error. This is the standard error. The standard error of R, okay, A hat is approximately equal to this thing. So we use that criteria that's under the assumption that the autocorrelation, that the kth autocorrelation of the residuals is equal to 0. So those are the bands that are shown in the ACF of the residuals in the plots that we have seen when we fitted ARIMA models already. Okay. Now, this autocorrelation test, just using those bands, is not valid for small lags. Okay, so that criteria to see if the sample autocorrelations are between those two limits is not valid for small lags. Okay, so for the first few lags, let's say k less than or equal to 4, that criteria is not valid because the residual autocorrelations are autocorrelated. I mean, we know that because we mentioned that when we started talking about the AR models. The autocorrelations of the residuals there exists autocorrelation in the residuals. So for small k, that's not a good criteria. That's why we use the other statistic. We use this statistic was originally developed by Box and Pierce and was defined as n minus d minus p times the sum of squares of the sample autocorrelations. Okay, and then Young and Box modified it, adding a term. So it instead of just considering n minus d minus p, they multiply by n minus d minus p plus 2, and then divided here the r sub k by the degrees of freedom, n minus d minus p minus k. That this k is the one that goes with this sum. Okay, so the Young-Box statistic is testing for different values of k the hypothesis that the first little k, capital K autocorrelations are 0 against the alternative that they are different from 0. Okay. So in essence, let me see if I wrote it down here. And we use this statistic to test the null hypothesis here. The null hypothesis. The null hypothesis would be that row 1 equal row 2 equal up to row sub k equal to 0 against the alternative that at least oh Jesus, I'm doing something wrong with my pencil here. At least one of row I with I equals 1 through k is different from 0. Okay, that's the alternative, and that's the Young-Box statistic, and that's what we see in that graph that shows the p-values for this test. So when we see this graph in the diagnostics, when we see the Young-Box statistic graph, we see what's listed here are the p-values, and they also print a 0.05 level here, 0.05 significance level. So if I have p-values less than 0.05, that is, we assume that then we cannot, we should reject this hypothesis. And that's computed for the first values of k. And if you look at other packages, for example, Minitab will give you the Young-Box statistic for k, for capital K equal to 12, 24, and 48. Okay. In the case of this software we're using with R, this package we're using with R, it gives us for different values of K, what are the p-values. And again, what concerns us here is more in the short term. So for smaller values of K, how those p-values behave. Okay, let me erase this thing. Now, if the residuals, what happens if the residuals, what happens if we have very small p-values at the beginning, in the first k-lags, k-lags? Well, then what we can do is we can actually use, let me try to erase this thing because it doesn't let me erase it here. Drawings. What we're going to use is we're going to work with the ACF of the residuals, and if necessary, we will compute also the PACF of the residuals to identify an ARMA model for the residuals, because identifying an ARMA model for the residuals will guide us on how we should correct the original model to avoid autocorrelation on the residuals. Okay. Let's look at an example. Suppose that the actual process is this one here, okay? Yeah, suppose that that's the actual process. Phi of B equals W or times applied to WT equals theta B of AT. AT is white noise. Now, that's the actual process. But suppose that we identify this model. We identify this model, and when we check the residuals, turns out that the residuals are not white noise. So when we check the residuals, they are not white noise. If this is a true model, and this is what we identified, we can use this information to modify the original model. Then, if this is not white noise, we identify a model for BT, for the residuals of this wrong model, okay? And suppose that then the BTs will follow this model. Okay, all I'm doing here is I'm taking theta prime B, which is this thing, and now WT, I know that I'm replacing WT by phi of B, BT equals to phi prime B, theta of B, AT. So that BT will follow this process. And this, knowing what type of process the BTs are following, the residuals are knowing, will let me to correct the original model. Okay, that's why this thing happens. I mean, theta prime B, BT is equal to phi prime B of omega WT, and that's equal to this thing here. Okay, and that gives us this expression. Now let's look at an example here. Suppose that I have a model that the true model is an MA2 model. Okay, so the true model is an MA2, 1 minus theta 1B minus theta 2B squared AT. But the model we identified is an MA1 model. Okay, we said no, but my model is an MA1 model, which is 1 minus theta B applied to BT. When I plot the residuals and the ACF of the residuals, then we'll see that the residuals are not independent. And then, or if we look at the Young box statistic, we'll see that the p-values are small for small lags. Then we'll observe that the BTs, the residuals, will follow an ARMA 1-2 process of this form. Okay, 1 minus theta B, BT equal to 1 minus theta 1 minus theta 2 B squared AT. So that will be the process followed by the BT, and that will lead me to correct and add a second order term in the moving average polynomial, because I was missing one. Okay. We'll see that when we analyze series, we'll check how the residuals look like. If they are correlated, then that will give us a hint on how to correct the model. Okay. Now, I'm going to do here just a couple of exercises, and then you will do the others. I'll do the annual ship population, and the glacial varves data. Now, these glacial varves are, they measure thickness of varves, which are varv sediments in a place in Massachusetts for about 634 years. Okay, that's 11,834 years ago. And because the thickness says a lot about the age of let's say of the last time, the first time that life appeared in that area or something like that. That's why they use these glacial varves. And then you do the analysis of the others, annual yield of straw chemical concentration in USGMP. We'll see how far we get today. So I'm going to start with the annual ship population. The script says ST08, construcción modelos ARIMA. ST08, construcción modelos ARIMA, and it's in bright space. It's this one here, ST08, construcción de modelos ARIMA. Download that script and download the data, the VARV data, and which other data they have told you that we're going to use now. Let's see. Download the annual ship population data and the glacial varves data. Annual ship population and glacial varves. So if you look at your data section, it should be annual ship population is this one here. So download that. And the glacial varves data. Glacial varves data. Okay. Download those two files and download the script. We'll do those two examples, and then you'll start working the others. I don't know if you'll be able to work the other examples today, but you can always have the weekend to do it. Okay. So let me know when you're done. Let me clean all this stuff. And run. This script also has the monthly Boston armed robberies data that we used last time. So just run the whole thing until up to line 50. Okay. Let's see. No, don't run the armed robberies again. Load the libraries, and then go straight to the annual ship population data in line 51.
Ready, teacher.
Ready? Okay, good. Now, here I'm reading the data, and if you see, there's two columns. One is the year, and the second column is the thickness of these glacial varves layers. Now, I make it a time series. So I start in 1867 and frequency 1 because I have one observation per year. If you look at the plot of the data, you can see that there's a trend. Okay. There's a trend, a downward trend on the series. And so this immediately, when you see something like this, you know that you're going to have to take at least one difference. Okay, so you need to take at least one difference. Now, here it's not easy to appreciate if we have non-constant variance. So we'll check with the computing the lambda, Box-Cox lambda, and that gives me 0.28. That's close to 0. Okay, so since that's close to 0, and I know because of the way the shape of this graph that I'm going to take one difference, then it makes sense to take the log. Okay, instead of just taking the data raised to the 0.28. Makes sense to take the log, because since I'm going to take a difference, I'm going to have the difference of the logs, which will be the log of the ratio of the thickness in year t divided by the thickness in year t minus 1. Okay, so I'm looking at the increase or decrease in thickness, essentially. I'll use the optimal lambda and see how the graph looks. And as you can see, there's the difference is not too noticeable, but it's different enough from one that to consider the transformation. But again, since it's close to 0, we'll work with the log. Okay. Now let's see here. Oh no, let's see. Now if you look at the graph here, essentially, no, that's not true. I thought I saw an improvement in variance, but I don't see an improvement in the spread of the data in time. So there may not be a need to transform the data. At least I cannot observe an impact in the graph of the data in terms of the variance. Now we'll try it again. We'll try it later, but for now we can decide to start working with the original data, because we saw the transformed data doesn't change much. So let's look at the ACF and PACF of the data. Well, we can see here that the ACF of the original data dies these are sheep population. I thought I was working with I don't know why I started talking about the barbs. We see that the ACF dies slowly. However, it's not that slow the way it's dying. But we saw in the graph that there's a trend. So that trend says I need to take a difference to make it to remove the trend and have stationarity. So I'm going to take I'm going to call D1 sheep to the first difference of D of sheep, and then I'm going to look at the plot. That's the plot of the first difference. Now it looks that it fluctuates around a constant value, and the ACF of the data is I have a significant lag here. This lag is significant, but that's lag 4. If we had, for example, quarterly data, then we would think that maybe something is happening there, but we don't. We have annual data. So there may not be a logical explanation for this thing. I would probably consider that's noise, but since it's large, this may be an indication that I have larger order terms in the moving average side, and here I have 3 significant lags in the partial autocorrelation. So having 3 significant lags here. And I can imagine, here you can imagine a pattern. Let me draw it here. See. Now, if you look at the table of behavior of ARMA models, since I see a pattern here, and I have 3 significant lags, I may have an third order or regressive model, but I also have a moving average term because of this pattern that I can see here, pattern of behavior in the ACF. So that tells me that I may have a MA term. So we'll start with the SARIMA with 3 autoregressive terms and 1 difference, because we're taking 1 difference of the data, and then 1 moving average term. If I do this thing, the diagnostics look good. Okay. Let's look at the diagnostics. They look good. This center around 0. The ACF has 1 significant lag very far away in the past. So that's of no concern. That's too far away. That's about 17 years away. Okay, so this is not meaningful. And the p-values for the junk box statistic look fine. They are all large, so that means that I cannot reject the hypothesis that the first 5, the first 10, and so on autocorrelations are 0. And there's very close to normality in the residuals. Okay. Now, if you look at the estimates of the model, we observe what? We observe that we have the 3 AR terms are non-significant, and the MA term is non-significant. Okay. The MA term is not significant. So the first thing I do is I'm going to remove one of the AR terms and see what happens. I'm removing the first term, so I'm just fitting an ARMA 211. Look at the values of the parameters, and now the AR1, the AR2 are significant, and also the MA1 is significant. Okay, it has a p-value of 0.015. Remember, these p-values test the hypothesis that the coefficient equals 0 against the alternative that the coefficient is different from 0. So a small p-value tells me that I can reject the null hypothesis. A small p-value tells me I can reject this null hypothesis. So the 3 coefficients are significant. What's not significant is the constant. So I can fit the model. In fact, it really doesn't matter if I leave it, but I can fit the model without the constant because that'll be more parsimonious. I have one less term in my model, so I specify the condition here in the function that no constant equal true, so that it doesn't fit a constant. And now my models, the 3 parameters are significant. I only have 3 parameters. And then I do I'm sorry, let me go back to my diagnostics. We go back to the diagnostics. We see that the assumptions seem to hold. Okay, we have large p-values, starting with the first lags, and that's a clear indication that I have independence of the residuals. I have randomness here. It shows here and it shows here also. This is confirmed. This confirms this graph, and I have normality. So this is a good model. Okay, that's a reasonable model. So I started with a more complex model, but then since none of the parameters were significant, then I start removing parameters. Okay. Now this is the VARB data. That's a VARB data that have remember, those are thickness. And if I look at the plot, if you look at the plot of this VARB data, here we can see that there seems to be different variance. Okay, I can imagine. Let me draw some lines here. I can imagine my variance around in this range, in this section, but then it goes like this section, and then it goes like this in this section. So I definitely have different variances depending on the period of time. So in this case, it will make sense to consider the transformation. Okay, here it's obvious that we need to consider a transformation. Let me take this thing off. Okay. Now I'm gonna do the box-close transformation. Okay, and that will be. I'll look at the ACF too here, although it doesn't make sense to look at the ACF in this case because we see an ACF that doesn't decay quickly to 0 because I have non-stationarity. In this case, the non-stationarity mostly due to the difference in variance. Okay, so I'm going to do the box-close transformation. This is the same function we've been using, but there's two methods that are used in this function. One is the Guerrero method, the other one is the log likelihood method, okay? The Guerrero method is the one that's preferred for time series, okay? And that's since I declare this object as a time series, Barb is declared as a time series, it will use essentially the Guerrero method. So Boxos lambda, it gives me 0.03. That's very close to 0. So in this case, it's clear that we should take with the log, the log of the varb. So I call log varb logarithm of the varb and make a plot of that. We see that there seems to be some behavior here. It looks like I have some type of pattern. I don't have everything fluctuating around the value. So that tells me that I should consider taking a difference. Okay, and I will take a difference. So I look at the plot of the difference, and now it fluctuates around a constant value. So I do not have a polynomial trend anymore. Okay, I don't have an adaptive polynomial trend. So I need to work with the differences. So I'll take a look at the ACF and PACF of the difference of the logs, which again makes sense because remember these are annual data, and the difference of the logs is the log of the ratio of the thickness in year t divided by the thickness in year t minus 1. So it's measuring essentially the change in thickness from year to year. I look at the ACF and the PACF, and now I can see very clearly that it looks definitely like this could be an MA model. Okay, this could be an MA model. You look at this thing, you see at the significance of this lag here. So this could be an MA model. That's the first model we're gonna attempt with the log data. And so it's one difference, and then an MA1 model, and see how it works. Okay. So look at the ACF2, and sorry, I'm going to mod 1 Sarima, and look at that thing. Of course, the only parameter is significant. Yeah, it is significant. I should add the no constant here, but anyway, if I look at the diagnostics here, this is not a good model. Okay. This is definitely not a good model because I have high autocorrelation in the residuals as proven by these p-values of the Young-Box statistic. So I need to correct that model. Now, remember what we said, that if we have autocorrelation in the residuals, then we can use the ACF to determine if we need to add terms. Since we have a strong autocorrelation in the first lag of in the ACF of the residuals, then that tells me that there seems to be strong dependence of from 1 year to the previous year. So that tells me that I should add an autoregressive term, because this is telling me I have strong autocorrelation between the residual at time t and at time t minus 1, okay, regardless of the time of what t is. So that tells me that I should include also an autoregressive term. So that tells me this graph is guiding me as to how to modify the model to get a better fit. So I will add an autoregressive term, okay, and I'll fit a Sarima with one autoregressive term, one moving average, and one difference. And now I can see the two parameters are significant. The constant is not, but I can just remove it with a no constant equal true. Okay, I'll just add it here, is no constant equal true. Repeat it again. Okay. Both p-values are very, very small. And if I look at the diagnostics, now my p-values for the junk box statistic behave correctly. Okay, so I have a good model now because I have randomness here, I have close to normality in the residuals, and my junk box statistic has very large p-values for all lags. I mean, the first 20 lags have very large p-values. So this is a good model. So the residuals from the bad model guided me on how to modify the model to fit correctly my data. Okay. So those are two examples. Let's see. Now I'll split it in groups. We have, it's 11:10. I'll give you 10 minutes. Okay, work only, just do the analysis of one of the series that I show here. Do the annual yield of straw. Annual yield of a straw. It's also in bright space. You can just follow this script and do the analysis for the annual yield of straw. I'll give you 10 minutes and we'll go back just to end the class. Okay. To create